Okay, so hello and welcome, guys. Um, as said, today I'll be going through this paper, High Resolution Image Synthesis with Latent Diffusion Models, which is also called Stable Diffusion for short. I think on Hanging Face, if you'll look for the API or the endpoints of the model, it's most probably called Stable Diffusion. If I remember correctly, yes, it is Stable Diffusion. Um, So again, by the authors of Ludwig Maximilian, University of Munich, and Patrick Isser from Runway ML. Um, so let's just go through this paper and think like what all is there. So I have not even like I have read this paper. I think a year back or something. And as we can see, this paper was accepted in CVPR, which is like a quite a big conference of computer vision. Yeah, so let's first go through the abstract and see what all is there. Good. By the way, before going through the abstract, let's do a quick uh, uh, touch and feel of the paper. Like, what all is there in the paper? How many pages are there? How do they look? And maybe get a sense of idea of what the paper would eventually talk about. So from figure to figure, I think would be the best. Um, so as usual, it will have an abstract and introduction, and let's see what what the first figure has. So just analyzing the figure, what do I feel is like? Okay, so there's input, and then there's their model, which is like f is equal to 1, f is equal to 8, f is equal to 16. So what is f, by the way? So we denote the spatial downsampling factor by f. Okay. What is meant by spatial downsampling factor? So what is meant by spatial downsampling factor is like um, how many. So let's say you have an output image, and how many times you would downsample it. Um, how many times you can downsample it to get that output image? Most probably that, but I need to look at it. I'm not too sure about what spatial downsampling factor that was here. Um, so we can see the results have kind of like PSNR and RFID actually. What are PSNR and RFID? These are some evaluation metric for particularly for the generative image models. So PSNR is like peak signal to noise ratio, and RFID is something like I don't remember what R stands for. So it's reconstruction. So it's reconstruction FIDs. So FID is basically the Frederick inception distance. So what do we mean by Frederick inception distance? So it's a so just going by what the label is or what it's being called. So it's called inception distance. And if you have done maybe one or two lectures in computer vision, then you may know the model called inception model, which is usually taken as a standard model. So what they will do is like they'll basically pass the generated image to an inception model network, and then take the outputs of that inception model and see a distance between that output and um, I think so. How would that FID be? Because there is no um, actual image, right? How is FID? So reconstruction. Okay, so it's so as of now. So just going through reconstruction FIDs. Reconstruction FID would mean there is an input and then there is a reconstructed image, right? So the input image you pass through the inception network, the reconstructed image you pass through the inception network. So and then take the some distance between the outputs of the inception network. So what would be the outputs of the inception network? So um, you can just take away the final layer, which may be for classification layer. So just take away that final argmax thing and do the rest. I mean, you have the numerical values of the final layer of the network, right? So you don't need to take the softmax. The softmax would convert it into probabilities. Before taking the probabilities, you have the numbers, right? You can take those numbers. So you got two sets of numbers, one for the actual image and one for the reconstructed image. Now you can take any form of distance. Um, so distance can be in any space and in any form. Uh, don't think in, so you can also take L2 distance, but I'm not too sure what the actual FID takes. Most probably it takes some form of KL divergence. And when I'm saying KL divergence, then I don't need to take off the final layer. So it will be taking numbers and then take softmax, then bring the probability, then you have a probability distribution. So input image probability distribution and reconstructed image probability distribution. So between these two probability distribution, if you want to find your distance, the best way possible is a KL divergence method to find the distance between these two probability distributions. Most probably FID stands for that. Um, but yeah, this is something which I look at. As I said, this video is a learning video for me as well, so that I know what all things I have to brush up to prepare for the next video. What about peak signal to noise ratio? Again, I think I have kind of forgotten what's peak signal to noise ratio, but we can again go by what the definition or what the label is. So peak signal and noise. So what would be a signal in an image and what would be a noise in an image? So noise, what I can think of is like a Gaussian random noise, a noisy image. What would be it look like? It would just smeared out things. And signal is basically assume sharp edges. So if image has got very sharp features, or like it's looking very sharp, I mean the borders are quite distinct, the features of the eye, the feature of, I don't know, maybe it's a house, then the grills of the window and stuff like that have got pretty defined boundaries. So when you have a very defined boundary, then what would have been going on? So in order to have a very defined boundary or a very good edge, um, I mean, just go back to edge detection algorithm and what it kinds of find out. So edge detection algorithm, if you have studied, or if you have just, if you can even think from your intuition, how would you detect an edge? Okay, that would map you to what would you define as a signal, and the opposite will be noise. So if so I'll just speak out how we define or how we get edges. So we get edges by taking translations of convolution, and then so assuming that it can be taken through by a particular kernel which has difference in the left and right side. So once we have this kind of kernel which has got different values, like different values in magnitude, um, not magnitude but in sign, I think, yeah, on the left and the right hand side, then it can actually go through the image, pass through the image one by one, and can detect an edge. Why? Because if there will not be an edge, then what would happen? The output of the convolution will be zero, because it's symmetric in the right and the left hand side, right? So the output will be zero, but if you have an edge, then the output won't be zero. So that's why after taking uh, convolution through this kind of filter, you would be only left with edges. So that's an edge detection algorithm. So that would mean that the gradient from right and left hand side. So what essentially means, while taking a convolution, a kernel which is like opposite in sign on right and left hand side, it essentially means you're taking fx minus f of minus x, right? uh, so if these values are like equal in magnitude, then you get a 0. on top. If they are like opposite in magnitude, then, or may not be opposite, but one of them is 0. Only one of them is 0. So fx minus f of minus x. One of them is 0 and one of them is not. That means an edge, right? And then if you divide by the distance, what would it be? So fx minus f of minus x, or even very standard case. So fx plus h minus f of x, just f of x, divided by, just divide by a scalar which is h, and let h tends to 0. What does that mean? I think you have the answers. It would be a differential of sorry, not a differential but a derivative. So uh, differential is just the top part, like del or delta of f, but derivative is with respect to another variable. Since we divided it with that h, and that h being in a particular direction, so I said on the first, I said, like I think minutes ago, that we'll divide, we have an fx minus of fx, and the kernel would go in a particular direction, so that means that there is a sense of direction as well. So it will be f of x divide derivative of f of x divided by derivative of x, so x being the direction. Let's move ahead. uh, so peak signal to noise ratio are calculated on ImageNet validation set. That's fine. So both of these things. So let's say there is a model. Now you need a particular data set, right? So all over the world, people would want to calculate the. I mean, take this as a datum, and then if they further develop another model, let's say stable diffusion 2, then what would they evaluate it on? So there has to be a standard data set, right, which they can, if they can reconstruct through their process, and these values are like better with their model, then they will say they beat stable diffusion. So that's why they're just setting standard that okay, we'll only take ImageNet validation set and then calculate these metrics. So again, I did not answer what was peak signal to noise ratio. So I said what would have been a signal, right? Sharp edges, distinct boundaries, or like maybe sharp difference of color or something like that. That can be a signal. Whereas noise, so noise can be like the derivative through all the directions at a particular point would be 0. That is, or approximately 0. That is the image. That is, at any point in the image, it does not has it lacks the sense of directionality, or it lacks any image feature, I would say. So that can be noise. So presence of image feature is signal, and presence of noise, and lack of any image feature can be termed as noise. And the ratio can be uh, um, ratio can be calculated, like if you have signal, you have noise, so you can calculate the ratio. I am still not sure how, I mean, why this metric would be um, good. This why this metric would be a good metric for for evaluation of reconstruction. Um, so can this metric be fooled? Is the thing which I'm thinking of. So if I have, yeah, if the image is like not that great, but just has the peak values, like the maxima of signal noise, and the maxima of signal to noise, the ratio is quite good, then I think this would fail. I mean, you just have a light leak, let's say a light, a strong light, like this strong light. So that would create a very sharp edge, you see, and then at some point very grainy or like very diffused kind of thing. So I think the peak signal to noise ratio would still be good. So I am definitely I don't think this is a very good metric, but I need to think more on, or maybe search the net on why this won't be a pretty good metric. Okay, good. What about the second diagram? So let's see. This one I was actually looking at while I was on my flight from Atlanta to Boston, but I could not make out like what does this image actually wants to say. So it says that I mean, first, I don't know why it says first we have a semantic compression and then a perceptual compression. So I understand that when you are compressing an image, let's say you're taking an image and converting it into pure noise. So first you take out the more important features, and then as the image start diffusing, less informative features are then taken out into the later stages. So that is something why we do scheduling in diffusion models. Now distortion would mean this opposite, right? So if in the early stages the distortion, I mean, okay, so again I'm a bit confused on what is distortion. Is it the difference between like one time step, like if there is an initial image and then you have to go to the pure noise, okay? So now you take baby steps in doing so. So is distortion the difference between the image at one time step and subsequent other next time step? So if that's the case, then the distortion would be high towards uh, towards the start, right? As I said, uh, I mean, you don't need to add a lot, or you don't need to destroy a lot from to get to pure noise when you are already there with a lot of noise. So then um, that can make sense, and the graph can also make sense. The distortion would be high. Bits per dimension, bits per dim. What has been? Has it been time? Then it would have been fine. Bits per dimension. Again, I need to look at it. I'm not too sure. And again, why latent diffusion model is somewhere here, and why autoencoders and GANs are here. I think this concept is pretty dense and pretty intuitive. So thinking about it right through and through would be difficult for me. Um, but I think if I go through the paper, like along with just not just seeing the image but also reading it, like maybe departure to latent space and stuff like this, like radar distortion trade-off, hmm, then maybe I can answer. So that's for later sections. First, just let's look at. So they have a little diffusion probabilistic model. Okay, so they may be working with diffusion probabilistic model. Mm, two-stage image synthesis. Okay, so they will be having two stages. So I don't know. Usually, what is a two-stage algorithm? Encoding and decoding is a two-stage algorithm. VAEs are two stages. VAE have two stages, but they talk about two-stage image synthesis, not so they'll synthesize image in two stages, which means both the stages will synthesize image, while just the VAE doesn't synthesize image in both the stages. It first compresses and then decompresses, so it's just one stage. So two-stage image synthesis would mean first you synthesize like a hierarchical VAE, like two VAEs. First you synthesize a fair image, and then you synthesize a perfect image or a super resolution image. So you have to synthesize two times. So that's there. We'll see later. If that's the case. Perceptual image compression. Yeah, this is the thing, right? Perceptual image compression. So I have to read through this one. Then we have this LDM over here. We condition LDMs either by concatenation or by a general cross attention mechanism. Okay, so here they just want to show what the general architecture would be, and how, but in particularly how they are conditioning their LDMs. So it seems like the paper would have a diffusion model or latent diffusion model, and then it will also have conditions. It's like the diffusion model itself would be conditional. What are the popular ways of conditioning a model? So what does conditioning a model mean? Conditioning means during inference you will provide that particular condition, and the generated object, with be it image or whatever, it has to follow that condition. Let's say, um, during training, you kind of figured out a way to generate images of 1 to 9, oh sorry, 0 to 9, which is MNIST. But during inference, if you train, if you'll infer a simple diffusion model, you're not too sure which image would pop out during inference. So in order to control the image generation process during inference, you need this controlling factor or conditioning. That is, you provide a condition that, okay, hey, I want to generate 4, then the model would generate 4. How would that capability be instilled in a model? Is something which is called conditioning the model. That is, during training you would, so everything is about training, right? If you have trained the model with such a task that you are also providing conditioning during training, then only you can ask the model during inference that, okay, now I'm providing you conditioning. This was the output which I have showed you multiple times during training, that when I put condition 4, like a, maybe a text or an image or like a number maybe. So when I put a number 4 and I give you, so whenever I'm putting a number 4, I have input and output in the generative model which are pretty much similar to the number 4 in image sense, like from MNIST training data. So during inference, when I'll just put that number 4 as a condition, which can be text or a digit, then the model will be thinking in that direction. Okay, yeah, during the training I have always went ahead with generating the number 4, because the output, because during training the output was 4, right? So if it was not generating it, you were penalizing the model, like, hey, you are wrong, my output was 4, you should have been 4. The model now learns to be 4. The weights of the model are aligned in such a way that it has to produce 4, like it has to give the maximum probability to 4. In generative science it will be very different, and I'm just talking about in like in sense of probabilities, or like in normal sense. uh, just looking at this, I would say schematic or architecture schematic or whatever. So it looks like, yeah, so it follows like this. So we have the input X, an encoder. It goes, my X goes through the encoder. Okay, so this is pixel space. So X is in pixel space, mind you. That means image. X is image, goes through the encoder, makes a Z. Z is a latent vector, I would suppose. Latent space. So latent space, so it should be a vector. It can be matrix as well. Matrix will be more difficult and will add more complexity. And will even give, I don't think it will give any benefit. Think about it. So yeah, this is my first question. Can the latent space be, what will be the difference between a vector Z and a matrix Z? Okay, yeah, and which one will you prefer and why? So now it says that in the latent space, that is the Z vector, but it will be vector. I think it should be vector. I mean, the answer would be there. Um, you can you can post in the comments this answer, um, and then we diffuse that uh, vector Z, go to ZT, that is at the end of the diffusion time step. Okay, so this is a diffusion model. This diffusion process is a diffusion model. That is, diffuse it to diffuse it in capital T time steps to a Gaussian noise or a random normal vector Z. That is if you will plot the values of this Z capital T, you would observe something which is similar to a probability distribution of Gaussian of that dimension. Okay, now what? Now we do the, so this was the forward step, now we do the reverse step. So I mean, prequel to is, it is a diffusion model. So if we know diffusion model, then z capital T would now reverse to your actual image. Okay, from pure noise. So from input image, go to pure noise. From pure noise, you have to go back to the actual image, but that will be in a iterative procedure. That is, you don't, neither you came to the final z capital T in one step, nor you will be going back from z capital T uh, to zt minus 1 in one step. So it will be uh, like a multi-step or multi-stage process. Okay, and that is what it's being showing here through, like, so in t minus 1 such processes, so this is like a small um, figure of this large figure. So you do this thing like z capital T to z capital T minus 1, t minus 1 times, where will you reach? So you took capital T steps to reach from z to z capital T, right? Um, so once you so if you exhaust z capital T, you reach z t minus 1. That's one step, and then in t minus 1 step, that is total of t minus 1 plus 1 is t steps. You will reach back z, right? Okay, reaching back z, you have a decoder which converts it back into the pixel space. Okay, interesting. But the main caveat is about the conditioning. How is the conditioning being given? So conditioning can be given as semantic map, text, representations, or images. What are semantic map? So I don't know if you have heard of semantic segmentation. So basically, image detection or localization or things like this have got various kinds of segmentation or basically dividing the image into various boundaries. Semantic segmentation is one of a kind of such division, um, where you basically um, construct boundaries or construct regions pixel wise. Um, so by the way, there's a difference between semantic segmentation and instance segmentation. In semantic segmentation, similar class object would be classified the same, but in instance segmentation, every instance of object will be given a different class. That is the difference between semantic and instance. So semantic, what will be semantic map? It will be just be that, so taking an image and then create a semantic segmentation. The map, the semantic segmentation map or the output is basically, so it will take away all the features, it will just color based on class. That semantic map can be given to this tau theta. So tau theta is what? Why is there a tau theta? Again, this is a question. What is the need of this? So the answer would lie somewhere in, think about what is zt and think about how these things are there. So is there any way you can marry zt or like any z? So basically zt goes in, zt minus 1 comes out. Now zt minus 1 is here. Now the second time zt minus 2 would be here. So all the z's, so this is a switch. Why is, what does the switch do? Let it be. I'll come later. I'll come to it later because I need to think myself as well. So yeah, so first up, so where were we? So in these input conditions have to be fed through tau theta. Tau theta would go to either to, so switch is there now, either to zt or zt minus 1 or whatever, or it will go through to the layers of the unit, the reverse process, whatever model is there. uh, like the actual model uses a unit more often than not. So and parameterize, so this is a parameterization of the reverse step diffusion model. You need to look at, or I can explain it later on, the why, what is this epsilon theta. This is basically the parametric form of the loss function of a diffusion model. What is mean by parametric form? So you can understand, like any probabilistic model, if you want to reach to um, an optimum value, you have to define it through parameters, right? Which will govern the probabilistic model to reach to an optimum value. I mean, what I mean to say is, you will form your equations in that, in the in that variable or parameters, and then you'll try to um, use some calculus, some form of calculus. I'm not just saying derivative or whatever. It will depend on what space we are working in. So you will use that calculus, matrix calculus, let's say, or tensorial calculus, and then optimize that value of theta in order to bring that loss function to a minimum. So that is what is called parameterization of a model. And here, fortunately, epsilon, or epsilon being the noise added at um, each diffusion step. So I said, right, the forward step is t times, so we add noise at each diffusion step. So here the parameter is epsilon theta, that is how much noise is added in the forward step is what the reverse step would want to predict. If it predicts well, then what would that mean? Think about it. Again, think about it. Pause the video, think about it. So if it predicts well, then that would mean that if you subtract subsequent noises from the noised image, you will get back to a somewhat similar looking input image, right? Somewhat similar looking input z over here, because it's a latent space. So that means you have to learn that process of like removing the noise through the image. So that is what parameterization of this epsilon with theta is essentially. um okay, yeah, so I'm saying, so where was I? So I said there is a switch, which means there will be two modes. So one, so maybe they trained a model while giving conditioning to z capital T, which is via concatenation, LDM via concatenation, or by a more general cross intention mechanism, that is providing the conditioning to the layers of the uh, reverse diffusion model itself, or the reverse diffusion unit. How would you provide this information? So they have written QKVs, so you understand, right? Where is this QKV coming from? It's all about attention. So what will happen? So just, I mean, think first. Pause the video. Think about it. How would you give this attention? How would you design something that gives this attention? So the core idea is you need to provide information to your model during training. As I said before, during training, if you provide this information, then the model is trained in that way, right? That it always needs that information in order to map your input and output, like in order to learn the mapping from input to output. So during inference, if you'll give that particular conditioning, it will be it will recall and say, okay, hey, during training you showed me this condition, then I have to follow this path, like the input and output will be this. So again, same thing. So think, how will you provide this information to the layers of the network in terms of attention, like QKVs? So essentially what would that mean is that um, basically what they might have done Okay, but instead of figuring out what they might have done, I think I should, in this next video, I should think more on how to actually think about it, like how to break the glass and think through. Like, I don't know, even I am not too sure about how to give that attention to it, but I think in the next part of this video, maybe I'll make one more part of like brainstorming. I'll brainstorm like from scratch, like how to give this information to this a neural network in terms of cross attention. Okay, so you retrieve back this x tilde, and this is like the reconstructed image which we are talking about in figure 1, I guess, right? So x, and then you can reconstruct back x tilde. But pure generation would mean that you go from this zt to any new x tilde. How would you know zt? So zt, as I said, was a random Gaussian, right? So you know what a random Gaussian looks like. Um, so I mean, yeah, you can just sample random Gaussian and then convert it into images. So this may be a bit more than what goes into your mind or into my mind, but I would explain it more better, because that's not nothing bad on your part. That's bad on my part, because I don't know how to explain it right now in 2 minutes or in 1 minute. Um, that's fine. So what about this figure 4? So this figure 4 is like, okay, so whenever you think about computer vision, you have to maybe don't memorize it, but if you read a lot of papers, you would know that, okay, celeb q, celeb ahq, all these data sets are pretty famous for computer vision, particularly in generation. ffhq as well, lsu embeds, imagenet. So these are all very famous data sets. So yeah, so these are samples which are trained samples from trained diffusion models. So I don't so these are not real people, but the model was trained on these images, so celeb ahq, and then it kind of generated these images. So what I was saying, right? So this is open generation, not reconstruction. So you are not given x and then reconstructing back x tilde. That was only for figure 1. For figure 4, it's free generation, that is open generation. So zt, which is like you sample from a random Gaussian and then convert it to some image. So these don't represent any actual celebrity or a person, although this kind of looks like, uh, I don't know. First, when it was zoomed out, I first thought it looked like Kevin Durant, but yeah, it doesn't. It can't. Again, why it can't? So why can't diffusion model produce the exact same image from the training data set? Is also a question which needs a lot of thinking, and it's a very good thinking exercise. Actually, it can, but the probability of that is very, very low. I can get back to that as well. Okay, I kind of missed figure 5 and figure 6 because of the essence of time, because these are basically FIDs. So I explained FID, right, versus the training step, and it's the inception score versus the training step. So FID is Frederick inception distance, and inception score would be just that uh, inception model's score. So maybe some kind of difference of inception model or something. I can get back to this. And speed. So these are all about speeds and throughputs. Uh, Rest of the images are more of like showing the capabilities of the diffusion model, or sorry, the latent diffusion model, rather than um, uh, so yeah, this is also, I can get back to these. So these are basically applications of the model. So as of now, I'll restrict this video to this, and we'll have more parts on this. So I think this would be a good exercise. Okay, thank you for joining in, and see you later in the next parts.